Now over on the carom board here, we were transferring sound, and sound bumps molecule on molecule. Now this here will show you how electrical current travels, and electrons don't physically bump, their fields bump. And so we will demonstrate that with this demonstration here. But first I want to explain some things. This is a piece of glass, a glass frame, framed by wood I should say, but it's glass on the bottom there. And writing on that glass we have a lot of little glass orbs. Those are little orbs that they put into the highway paint to reflect your headlights back to you from when you're looking over the hood of your car. That the light comes into the little glass orb and comes right back to your eyes. And that's why you can see the line of paint on the highway. And it reflects the color of the paint it's embedded in. So you can make any color of reflecting paint by having these little clear glass beads or orbs, drop them into the paint when the paint is at the right consistency. But for my purpose here, I use it for a dry lubricant. It makes these electrons very lively. The fact of the matter is electrons need a little control, so I'm going to put a piece of glass over the top of them, otherwise they get a little unruly sometimes. Now, this is very representative of a circuit, because here we have electrons, and here we have holding this iron ring. Where they represent electrons, they're actually magnets, and they hold to this iron ring because magnets like to hold uptight to iron. So if I push one magnet here, you'll see the electrical current go all the way around. So let's see what happens. See that energy that I put in this one electron went all the way around. Now that is the electrical current, not just the movement of the electron, but the electron's exchange of that energy. So it's the energy that's the electrical current, and these are just the electrons that the energy is employing. Now electrical current travels at about almost the speed of light. Usually there's some retarding factor, so it could travel maybe only anywhere from 66 to 95% the speed of light. So when I'm speaking about electrical current and the speed of light, I use that interchangeably because there's so many factors involved that can change different things, resistance and things like that, can change speeds. So I just use that interchangeably, but there is a definite retardation in a conductor. So let me show you how DC works. DC stands for direct current. So if I move this electron, the current would all the way. But if I didn't get another electron in the backside of the circuit, then I'd run out of electrons immediately. Now this circuit is just a little bit of demonstration circuit that I use in the office here, but it could be miles long, and you still have to bring the electrical current around to the backside to get resupplied electrons. Now that's not necessarily true of AC current, because all AC has to have is a bit of a length of wire long enough so that it can go to one end of the wire and back again in the frequency time. So the slower the frequency, the farther it can travel. Alternating current in house current, 60 cycles a second, can travel 3,100 miles in 1/60th of a second. But it goes 1,550 miles one way and comes back 1,550 miles. So in order to accommodate AC current, you'd only have to have a piece of wire 1,550 miles long, which is rather a ridiculous figure when you're thinking of, I'm thinking more of antennas that are made with elements that the current is driven to one end of the element and then comes back again. Now, for instance, channel 3 has a wavelength of 16 feet, and so the resonant length conductor for channel 3 would be 8 feet long. So it go 8 feet one way and come back 8 feet, and that's the full 16 feet. And so all elements, resonant elements for channel 3, that's TV channel 3, would be somewhere in the neighborhood of 8 feet, depending on the resistance of the conductor and other factors like that. But electrically, it would be 8 feet long. Now, talking about alternating current. Uh, well, let's go to DC current again. If I move this here, like I say, I have to get more electrons. But if I had a motor setting over here on this side of the circuit, as that energy passed through there, it would create magnetic fields around the coils and cause that motor to turn. And so I just keep receiving from one side, and that would be flowing on through that motor to be a DC motor. If it was AC, as the energy went one way through it, that caused the motor to turn, and then it would have to reverse the armature or whatever to make it pick it up from the other side so it would come back through. Otherwise the motor would just sit there back and forth like the current did. But if you reverse the current in the armature, then it can come back through and keep the motor going in the same direction. So again, like I say, this is a very good representation of how electrical current operates, and it's rather visible. It's, in other words, something you can understand quite readily. Now, this here display is good for a lot of other purposes, and one of the purposes that I want to show you is a new model for the atom. The current model for the atom that orbits electrons is not a valid model. It just can't operate. So in order to get something that can operate and show how everything operates related to electrical current, I had to develop a new model for the atom. And so this will show you is what I call the spring atom. But before I go into the actual building of the atom in this here open spot, I want to mention several things. One, the force of gravity, as far as I can recognize, is a one-way force of pulling things together, basically protons to proton. A neutron is only an electron and a proton attached to each other, but the protons are 1,840 times as heavy as the electrons, so they comprise most of the weight of the Earth. And that, like I say, it's a one-way force of attraction of mass to mass. That's gravity. Now, magnetic field, if you take two magnets and you put them together, north pole to north pole, they repel each other, and you really can't hardly push them together. But the fields are bumping. The fields around these magnets are bumping, not the magnets themselves. And when they do, these fields just squash out and they go up flat. They won't cross each other. Now, if you turn them around the other way, south pole to south pole, they do the same thing. But if you turn north pole to south pole, like this, they'll go together and they make a longer, stronger magnet. Now, electrons and protons will repel each other. Electrons will repel electrons. You push a whole bunch of electrons into an area and they want to spring back out of there. They're flexible. The fields are flexible, and so they build up pressure and ready to spring back when they have an opportunity. The protons will do the same thing, but the proton is so much heavier than the electrons that it's hard to move them. Electrons are very easy, so you can drive electrons at the end of a conductor and build up electrical pressure. But again, like I say, the protons don't do much moving because they're heavy. But when you turn an electron and a proton, put the electron and proton together, they don't make a stronger particle, a higher charge. The charges cancel each other, and they make the neutron. So the neutron is simply an electron and a proton attached to each other. Now, several years ago, I wrote in my books that neutron could be an electron and a proton welded together. Then I read a chart in Isaac Asimov's physics book that said that the half-life of a neutron was about 17 minutes. They put it in seconds. This is 1,030 seconds. But anyway, I recognize minutes better, so it's about 17 minutes for the half-life of a neutron. And when they separate into a proton and an electron. So that added another dimension to what I was saying, is that they aren't welded together, they're just drawn together, attached to each other. and they can be driven apart again. And if you drive an electron free of the proton in a neutron, you'd have an active electron. And that active electron can't reattach to that proton until it gets rid of all of its heat, because heat is what drives electrons back and forth. And there's very few places on Earth that you can get rid of all the heat and not get some back. So that electron's going to keep bouncing back and forth toward the proton and back away from it. And if you have a proton and an active electron, what do you have? You have the hydrogen atom. So you could take protons, take neutrons I should say, and drive the electron loose from that, so you have a proton and electron, create the hydrogen atom, and you could create all the elements of Earth simply from the way you combine the hydrogen atoms. And so everything then is combined of simply protons and electrons, and a neutron is simply an electron and a proton attached to each other. Now, the atom that orbits electrons around the nucleus, as I said before, is an impossibility. It just can't operate. And so we have to do something about making a better atom. See, they can't even describe heat properly with that model of the atom, because they can't permit the atom to expand. If the atom expanded, all the orbits would be off. So they have to speed up every electron and every atom of the Earth and the sky to make the electrons make it around that nucleus in the time it had to get around there. If they speeded it up too fast, it would fly out, and if they slowed it down too much, it would pull into the nucleus. So in order to describe heat then, and I would recognize this, that they're still currently teaching it this way, they say that heat is molecular motion. Heat is not molecular motion. Heat is electron motion inside the atoms, and the atoms themselves expand. And so what I'm going to do with this here model here is to show you the action involved in how atoms operate. So what I have here is a nucleus of protons. And I'm going to set it in the middle of this here area here. And I'm going to lock it in with another magnet on top of the glass so that it stays in position. Otherwise, it would drift over and attach to some of these electrons, because these are all protons. And if it drifted over, it would attach to the electrons of the neighboring atoms. Now, I was unable to use electrons or protons to demonstrate this, so I use magnets. And they're very representative of what takes place, so it's a very good example. Now, these are the electrons of the neighboring atoms. So I'm going to build this atom, and I'm going to turn electrons loose in here and let them orbit. They can't go to the neighboring atoms because they're going to be repelled by the neighboring atoms. So let's just see if we can orbit some electrons. And this is what they say atoms do. They orbit electrons. Now I'm going to take this little thing and lock these together. I don't have to do this, but it keeps the electrons from moving back into the atoms in this direction. And I'm going to set these magnets down as representing electrons, and I'm going to set them down and I'm going to orbit them around that nucleus. I'm just letting the repulsion of these magnets push them in. That's how long an electron would orbit a nucleus. You really recognize the impossibility of orbiting electrons, which are negative charges, around protons, which are positive charges. That's not, the laws of mass and motion are not the laws that operate inside the atom. There's other laws that do that, and I'll show you what they are. You notice that they're starting to form rings around there? The model of the rings isn't too bad. It's just the action that is not properly analyzed. Somebody looked out into space, they saw the sun and the planets, and they said, well, it must be the same down inside the atom. In those days, they couldn't see inside the atom, and so that was just a starting point. But they should have discarded that years ago. It seems like that they're very slow about making changes. I guess if it works, why fix it? But they can't describe everything if they don't have a good model. So I'm going to take this here out of the way. I don't need it. That was just to lock that down. I'm going to show you that this atom has a nucleus, has electrons is peripheral around the nucleus. They can't go to the neighboring atom because the electrons are there. They can't get into the nucleus because the first electrons that went in there attached to a proton and created the neutron. And so the neutron then becomes a barrier that prevents the rest of the electrons from going into the atom. So I can just shake this and they can't get in there. They're confined in this space. You'll notice that the atom has size to it, but it's not due to orbiting of electrons. It's due to simply the repulsion of electron to electron. Now, as this atom sits here, it's cold. There's no action in there at all. So it would be considered an atom at 273 degrees, that would be minus 273 degrees centigrade. It's absolute zero, with no action. Now, with no action in there, it'd be very simple to have superconductivity, which you could run electrons in and they just move on through because there's no back and forth action. As soon as you activate those electrons, it's very much more difficult to start pushing things straight forward through there because they're going back and forth. And that's why when you add heat to an atom, it loses that superconductivity. You still have the repulsion of electron to electron here as you're pushing them in there while they're quiet. But as soon as you get them activated, it's hard to move them forward through the through to the next conductor. This could be an atom in a metallic conductor. But all atoms would operate the same. If the electrons couldn't go to the next conductor, at least they could be pushed over to that far side of the atom. Now, there's several ways to activate those electrons. One way would be to push electrons in this way, and when you do, push electrons forward. In other words, you push them in a straight line, pretty much like the caroms did over there on the carom board. So that would be the electrical current, and that would activate electrons and create heat. Another way would be to run magnetic fields across the electrons. And now these electrons would be inside of a conductor, and so run this field across, the electrons run sideways out of the way of the field. That's known as a transverse action. They know that electrons run sideways, 90 degrees to the direction of travel of the magnetic field. But they can't do this with the orbiting electrons. So I'll show you how they run sideways here. You notice that it's running sideways in that, like that. That's because they're getting out of the way of this magnetic field. Now, there's two ways of heating this atom. The third way I see is just to shake the whole atom. Like this. When you move an electron, it creates a magnetic field around its path. When it comes back on that same path, it creates an opposing field inside that first field that drives it off. That's what radiation is all about. So when an atom is receiving more energy than it's giving off, it's getting hotter. And when it's giving off more it's receiving, it's getting colder. But there's always action inside of an atom as long as there's any heat involved. So that's a pretty good description of heat. It's a pretty good description of electrical current. And this is the best model that, as far as I'm concerned, has ever been developed. And I had to develop it right here because I had to demonstrate what I see happening. So we'll think about this a little bit more. I'll give you time to think about it, and we'll come back to this a little later or go on to some other things. Well, there's several other things that I should be saying about this atom. And one of them is that the arrangement in the interior of this atom is not limited to orbiting. The nucleus doesn't have to stay dead center and the electrons go around it. So you can arrange it any form you want inside there. It can be arranged by outside forces. So in my books, when I do some writing about the atom, I show hot air balloons that will show the gondola down low in the balloon and the emptier part being up high. If I lift this up like this, the nucleus will go to the bottom because it's heavier. And so the emptier part of the atom would be up. If you could see that atom expanding and rising in the atmosphere, I'm pretty positive you'd see that nucleus is down low in the atom and the emptier part of the atom would be above. There's no limit to the expansion of this atom, so it can, the more active the electrons are, the bigger it will expand. When it expands up into near